Good evening, all of you. Today we are going to discuss a topic called P block, which has tremendous significance as far as competitive exams are concerned. It nearly carries a weightage of 15%, as many as you can say 15 out of 100 questions. So, let us look at how to draw any structure. How to draw any structure. We have to look at how to draw any structure from which you will be able to find the number of sigma bonds and pi bonds. For this, there is a very simple procedure. You can say H, F, Cl, Br, I, O minus, wherever they form one bond. Wherever they form one bond. And oxygen, wherever it forms two bonds. Oxygen, wherever it is, forms two bonds. And any plus in a group, suppose you have a positive species in a group, any plus accepts a pair of electrons, accepts a lone pair of electrons from, of course, the central atom. And any other minus other than O minus, any other minus donates a pair of electrons to the central atom. If you have understood this, we can apply this in many cases. Hydrogen, fluorine, chlorine, bromine, iodine, wherever they form one bond. You look at it, how will you draw the structure of SO3? What is it you have in this? One sulfur, the central atom, and three oxygens. Right. So, what is it we have just said here? Oxygen, wherever it is, forms two bonds. Therefore, you have a double bond O, a double bond O, and a double bond O, from which you can conclude that sulfur is forming 3 sigma and 3 pi bonds. Where are the pi bonds? Of course, these 3 are the pi bonds. So, SO3, sulfur in all is forming 6 bonds, 3 of them are sigma and 3 of them are pi. So, this is how you can draw the structure of all molecules. SO4 2 minus, how will you draw? SO4 2 minus, 1 sulfur, 4 oxygens, which is there for all of you to see, 1 sulfur, 4 oxygens, 2 of them are minus. So, put 2 minus here, O minus, O minus. And what is the role of oxygen? Oxygen forms 2 bonds. Oxygen again forms 2 bonds, O minus forms 1 bond, 1 bond. So, SO4 2 minus sulfate ion contains 6 bonds, 4 of them are sigma and 2 of them are pi, 4 sigma, 2 pi. How will you draw the structure of BF4 minus? 1 boron, 4 fluorines, one of them is a minus. What is the role of fluorine? Fluorine forms 1 bond, all of us know. And what is the role of any other minus other than O minus? Here O minus forms 1 bond, other than O minus, F minus donates a pair of electrons to the central atom. So, NH4 plus, how will you draw the structure of NH4 plus? You have 1 nitrogen, 4 hydrogens, one of them being a plus, H plus. What is the role of hydrogen in a group? Hydrogen forms 1 bond with the central atom. And what is the role of plus, positive species in any group? Positive species accepts a pair of electrons with a coordinate covalent bond. So, you can say whenever you have a plus or a minus other than O minus, you can always predict a dative bond. NH4 plus, BeF4 2 minus, BeF4 2 minus, BF4 minus, AlF6 3 minus, SiF6 2 minus. So, all of them indeed contain dative bonds. Other than O minus, any other minus should donate and form a dative bond. Any other plus should accept and should form a dative bond. So, that is how we can easily predict the presence of a coordinate covalent bond, which is called dative bond. Right. Second, first procedure is over. How to draw any structure. Suppose you have an oxy acid like H3PO4. Why do we call it oxy acid? It has both oxygen and hydrogen. A compound that contains both oxygen and hydrogen is called an oxy acid. So, you have one phosphorus, 3 OH groups. How do you know that 3 OH are there? 3 OH. The rule for number of OH groups is equal to number of OH groups in any oxy acid. Number of OH is equal to number of hydrogens present. Of course, except for you have 3 exceptions. You just forget them. H3PO3, H3PO2, H3BO3. If you ignore these 3 acids except H3PO3, H3PO2, H3BO3, all others, number of OH is equal to number of hydrogens present. Since you have 3 hydrogens, you take 3 OH and 1 oxygen is remaining, and you know oxygen forms a two bonds, double bond. So, what about these 3? They can be discussed later. This has only 2 OH groups, this one has only 1 OH group. Of course, this has 3 OH groups. Okay? Strictly speaking, this is not an exception to this particular number of OH rule. So, you can say this is not an exception, but this is an exception in some other place. We will come back to that later. Now, how will you draw the structure of H4P2O7? H4P2O7. H4P2O7. You have 2 phosphorus. Take both the phosphorus. 4 OH groups. How do you know 4 OH are there? Number of OH groups is equal to number of hydrogens present. Since you have 4 hydrogens, you opt for 4 OH groups, OH, OH, OH and OH. What else are you left with? 3 more oxygens. Therefore, 1, 2, 3. Oxygen forms 2 bonds and the central oxygen also forms 2 bonds. So, the number of sigma bonds, pi bonds, POP bonds, all such questions on this acid could be answered. H4P2O7. N2O5. For nitrogen, more than 3 bonds, there should be 1 dative bond, coordinate covalent bond, when nitrogen has more than 3 bonds. Suppose you need to draw the structure of NO3 minus. 1 nitrogen, 3 oxygens, one of them is a minus. And what is the role of oxygen? We already discussed oxygen forms 2 bonds. O minus forms 1 bond. And nitrogen's quota of 3 bonds are over. We already discussed nitrogen can, for nitrogen more than 3 bonds, 1 dative bond. So, you put this as a coordinate covalent bond, 1 dative bond. Here you are. So, that is the structure of NO3 minus. So, in compounds of nitrogen and oxygen, you may predict a dative bond if nitrogen happens to form more than 3 bonds, NO3 minus. And what about N2O5? N2O5, 2 nitrogens, 2 central atoms, 5 oxygens, distribute them equally, 1, 2, 3, 4 and 5. Oxygen forms 2 bonds, 2 bonds again, and nitrogen donates a pair of electrons to oxygen. Why did we take a dative bond here? Look at the rule. For nitrogen more than 3 bonds, 1 dative bond. And last rule, try to avoid lone pairs as far as possible. Try to avoid lone pairs of electrons as far as possible. H3PO3. We already discussed that is an exception. It doesn't have 3 OH groups, and that is indeed true, and we will see why. Phosphorus, you take 3 OH groups. By doing like this, you are allowing a lone pair to be present on phosphorus. Here in this case, phosphorus has a lone pair, and we should see that lone pairs are avoided. How can we do that in this particular case? Make one oxygen directly bonded to phosphorus and one hydrogen directly bonded to phosphorus. So, this is the wrong structure, this is wrong, and what is the correct structure? Take one phosphorus, just take 2 OH groups and let the third hydrogen be directly bonded to phosphorus to avoid lone pair. So, why is this wrong? Why is the structure of H3PO3 wrong? In this, there is a lone pair which will repel the bond pairs, and within a few minutes we will discuss the effect of lone pairs on molecules. Okay. So, I have taken one of the hydrogens directly bonded to hydrogen, and this is the correct structure, that is the wrong one. Try to avoid lone pairs as far as possible while writing a structure. And now, how to find hybridization of any central atom? H is equal to V plus M minus C plus A by 2. Hybridization of non-metals. So, this rule holds good in most of the cases. Maybe 1 or 2 places this may not be very much useful. We definitely will have an alternative later, but let us look at most of the molecules. V, number of valence electrons of the central atom. Number of valence electrons of the central atom. Most of the time, number of valence electrons is nothing but the group number in which the particular element is present. Number of valence electrons of the central atom. M, number of monovalent atoms. Number of monovalent atoms. So, we have to ignore oxygen, which generally forms 2 bonds. So, oxygens are ignored because it forms 2 bonds. C is charge of cation, A is charge of anion. So, to say if you have a positive charge, you subtract that. If you have a negative charge, you add that. C is cationic charge. A is anionic charge, charge of the anion, anionic charge. So, after doing all this, if you happen to get H as 2, the hybridization is said to be sp, 3 sp2, 4 sp3, 5 sp3d, 6 sp3d2, like that. It goes on sp, sp2, sp3, sp3d, sp3d2, sp3d3. So, let us apply this principle, hybridization of non-metals. Boron trifluoride. What is the hybridization of boron in boron trifluoride? Boron belongs to third group, valence electrons 3, and you have 3 fluorines, 3 plus 3 by 2, you get 3, which is nothing but sp2. Third group plus 3, 3 plus 3 by 2. How about carbon in methane? Hybridization of carbon in methane. Carbon belongs to fourth group with 4 valence electrons and 4 hydrogens. So, 4 plus 4 by 2, which is nothing but 4, and you get sp3 again. SO4 2 minus. How will you find the hybridization of sulfur in sulfate ion SO4 2 minus? You already know sulfur belongs to sixth group, 6 valence electrons, and oxygens have to be ignored. Since they are divalent, forget oxygens. So, 6 plus 0 plus 2 by 2. Why have I put 0 here? Even though there are 4 oxygens, we are not going to consider them. 6 plus 0 plus 2 by 2, 8 by 2, 4, which is nothing but sp3. XeO3, what would be the hybridization of xenon? 8 plus 0 by 2. Why is it 8? Xenon, you know, has 8 electrons in its valence shell. like all other noble gases, they have 8 electrons in the outermost shell. So, 8 plus 0. If the 3 oxygens, they are not considered. It is just a formula, or you can say it is a shortcut. It is not that much of any concept, but it will make your life easy in finding the hybridization. One question on hybridization will be there in all exams, as you know well. So, 8 plus 0 by 2, 8 by 2, 4, sp3. BF4 minus once again. Boron belongs to third group, 3 plus 4 plus 1 by 2. I repeat, if you have a negative charge, you add the charge, 3 plus 4 plus 1 by 2, add the negative charge, and effectively you get 4, and that once again is sp3. The hybridization of boron in BF4 minus is sp3. NH4 plus, ammonium ion, NH4 plus, 5 plus 4 minus 1 by 2. Nitrogen has 5 valence electrons, 4 hydrogens, 5 plus 4 minus 1 by 2, 9 minus 1 by 2 happens to be 9 minus 1 by 2, 4, once again sp3. So, next. That is how you can find hybridization of so many molecules, and in the exercise that follows this lecture, we will answer some questions given in past exams. H2O, the hybridization of oxygen in H2O, 6 plus 2 by 2. Oxygen here is a central atom. I ask you to ignore oxygen not when it is a central atom. When SO3, when sulfur is central atom and 3 oxygens, I asked you to ignore these oxygen, not this one. Here oxygen is the central. You know how to draw the structure also. Oxygen central atom, 2 hydrogens, they form 1 bond each. So, 6 plus 2 by 2, 4 sp3. Next, for carbon only, no pi bond, sp3, 1 pi bond sp2, 2 pi bonds sp. This is for carbon only. So, if you have a molecule like this C, several carbons. So, what is the hybridization of this particular carbon? This particular carbon, 2 pi bonds sp, 2 pi bonds sp, 1 pi bond sp2, 1 pi bond sp2, 1 pi bond sp2. But this carbon has 2 pi bonds sp. This carbon has 1 pi bond sp2. So, compare the rule again. For carbon only, no pi bond sp3, 1 pi bond sp2, 2 pi bonds sp. So, here this carbon has 2 pi bonds, 1, 2. It is a triple bond, means 2 pi bonds. Here it is not a triple bond, but still the carbon has 1 pi bond on either side. You have a pi bond there, you have a pi bond here. So, 2 pi bonds sp. This is for carbon only. And there is a one concept called d pi p pi bonds. Very simple concept, d pi p pi bonds. Pi bond in which d and p are involved, d orbital of the central atom and p orbital are involved, d pi p pi. For example, what is it we already knew about SO3? SO3 has 3 sigma bonds and 3 pi bonds. If you go back to the structure part, you know, S double bond O, double bond O, double bond O, 3 sigma, 3 pi. So, sulfur is in all forming 6 bonds. So, you write down the excited state, 3S1, 3px1, 3py1, 3pz1, 3d1, 3d1. This is the excited state of sulfur, in which you see 6 unpaired electrons, 1, 2, 3, 4, 5, 6. You have 6 unpaired electrons, and now this is the excited state of sulfur. Otherwise, the ground state of sulfur is like this, 3s2, 3px2, 3py1, 3pz1. This is the ground state of sulfur, in which sulfur can form 2 bonds only comfortably with 2 unpaired electrons. It may at best form 2 bonds like in H2S, but SO3 means you need to form 6 bonds, and what do you need for bond formation? An unpaired electron. So, there are 6 unpaired electrons only in the third excited state of sulfur. Is it the third or the second? Let me see. First excited state 3px2 3py1. This is the first excited state. If you excite the electrons from 3px2 3py, first excited state, second excited state. So, second excited state of sulfur. This happens to be the second excited state of sulfur. So, here I need to form 3 pi bonds. So, leave 3 pure orbitals for pi bonds. You have sp2 hybridization, and these 3 orbitals are pure orbitals for pi, pure orbitals for pi bond formation, pure orbitals for pi bond formation. Okay. So, these 3 are given for pi bond. So, you can see DD, 2 d orbitals are participating, therefore, you will get 2 d pi p pi bonds. What does that mean? Sulfur contributes 2 of its d orbitals and 1 of its p orbital for pi bond formation. So, this is p, forget this dd. So, d pi p pi bonds. What is a d pi p pi bond? A pi bond in which d orbital of the central atom and p orbital of the terminal atom is formed. So, let us illustrate just one of the pi bonds of SO3. S double bond O, double bond O, double bond O. Sulfur is forming 3 pi bonds. One of the pi bonds formed by p orbital of sulfur and p orbital of oxygen overlapping. This is p and this is p. This is called p pi bond. So, this is over. P orbital of sulfur, p orbital of sulfur and p orbital of oxygen. But what about these two? D orbital of sulfur, d orbital of sulfur and p orbital of oxygen. So, this is a d orbital, this is a p orbital. So, this is called d pi p pi bond, d pi p pi. Okay? You need not be very particular about this drawing, don't worry. Sulfur, d orbital of sulfur, d, and p orbital of oxygen, d orbital of sulfur and p orbital of oxygen, p. So, this is called a d pi p pi bond. Next, regarding shapes of molecules, it all depends on the number of lone pairs. Number of lone pairs. How will you find the number of lone pairs? Number of valence electrons of the central atom, minus number of electrons used in bonding divided by 2. It is very simple. How many you have spent, how many electrons you have and how many of them you have spent divided by 2 will give you the number of unused electrons, which is called a lone pair, number of unused electrons. For example, NH3, nitrogen has 5 electrons, 5 valence electrons, because it belongs to the 5th group. 5 minus 3 divided by 2, ammonia there is 1 lone pair, NH3. XeF2 will have a little too many lone pairs. How will you calculate? 8 minus 2 by 2. 8 minus 2 by 2, 3 lone pairs. SnCl2. How will you find the number of lone pairs? Stannum belongs to 4th group. 4 minus 2 by 2. 1 lone pair. So, number of lone pairs present makes a lot of difference to the properties of a particular molecule. If a molecule has lone pair, its behavior is totally different from a molecule which doesn't have a lone pair. So, finding the number of lone pairs and finding whether a lone pair is present or not has utmost significance in chemistry. Don't you ever neglect that. SO3, do you have a lone pair? Sulfur, 6th group, 6 minus 6 by 2. Why 6? Each oxygen uses 2 electrons by sharing double bond O, a double bond. Therefore, SO3 hasn't got any lone pair, 0 number of lone pairs. SO2, sulfur once again belongs to 6th group, 6 minus 4 by 2, 6 minus 4 by 2, 1 lone pair, SO2. Okay? So, this molecule has 3 bond pairs and no lone pair. This molecule has 2 bond pairs and 1 lone pair. So, when you ought to talk about the shape of SO2, you should say 2 bond pairs, 1 lone pair, which anyone perhaps will understand. 2 bond pairs, no lone pair, like this, a linear. 2 bond pairs, no lone pair, BeCl2 will be linear. 2 bond pairs, no lone pair. But SnCl2 is not fortunate enough to be like this, SnCl2. BeCl2, the 2 chlorines are linear, but SnCl2, the chlorines cannot be linear to each other. Why? Here is a lone pair on stannum which repels the bond pairs. This is a pair of electrons. Bond pair also means a pair of electrons. Whether it is a lone pair or a bond pair, after all, it is a pair of electrons only. It is only a pair of electrons. Therefore, what exists between a pair of electrons and a pair of electrons? Repulsion. Negative charge, there can only be repulsion. So, 2 bond pair, 1 lone pair, 2, 1, it is said to be bent or angular. Bent or angular. 3, 0, 3 bond pair, no lone pair, as in the case of SO3. This is trigonal planar or triangular planar or plane triangular. Trigonal planar. They can safely adjust themselves in a planar manner. The 3 molecules, the 3 atoms of sulfur, they can adjust in a planar manner. So, we can have a list of what shape a molecule would have. 2, 0. What do you mean by 2, 0? This is bonded pairs, number of bond pairs and number of lone pairs. Number of, depending on bond pairs and lone pairs, the shape is decided. 2, 0, linear. 2, 1, bent or angular. 2, 2, it is called V shape. No problem in calling this as also. V is also bent. Suppose there are 2 straight lines like this, you call them linear. If there are 2 lines like this, it is bent or angular. It is bent or angular. If V shape also means it is also bent or angular or V shape. So, there is no harm in calling it angular. 2, 2. Then 2, 3. Once again linear. 3, 0. Trigonal planar. I think you can copy this while I am writing them. 2, 0 linear, 2, 1 bent or angular, 2, 2 V shape, 2, 3 linear again, 3, 0 trigonal planar, and 3, 1 is pyramidal. 3, 2 T shape. 3. What do you mean by 3, 2? This is the heading, don't forget this. This is the number of bond pairs and this is the number of lone pairs. 3 bond pairs and 2 lone pairs. When I say bond pairs, you have to consider the atoms only. You need not consider the pi bond. For example, SO3, don't think that there are 6 bond pairs. So, you should consider only the respective position of the atom. So, of course, there are 2 bonds here, but you consider only both of them as 1 bond only. You can say it is 3 bond pairs, SO3. 3 2 has T shape. 3 4 0 tetrahedral. 4 1 distorted tetrahedral, or seesaw. 4 2 is square planar. 4 2 is square planar. 5 0 is trigonal bipyramidal. 5 1 square pyramidal. 6 0 octahedral. 6 1 distorted capped octahedral, distorted or capped octahedral. 7 0 the last one, pentagonal bipyramidal. Two zero linear. Let me supply examples. 2 0 linear BeCl2. BeCl2 2 0. If there are any lone pairs, I will mark them. Since I have not marked any, you can say there is no lone pair. BeCl2 2 0 linear. SnCl2. I told you that I will mark the lone pairs myself. Now you say 2 1. 2 1 bent or angular. 2 bond pairs, 1 lone pair. Bond pair means 2 guessed atoms. Guess. The incoming terminal, they are called guess. They are called bonded atoms. 2 guess. 2 2 H2O, you can see 2 bond pairs. This is a bond, this is a bond, this is lone, this is lone. 2 bond pairs, 2 lone pairs. 2 2 2 3 XeF2. XeF2, you have too many lone pairs here. 2 bond pairs, 3 lone pairs. 2 3. So once again linear. 3 0 trigonal planar boron trifluoride. There are 3 surrounding atoms, guessed atoms, terminal atoms. This one is called the central atom. This is central, these 3 are terminal. 3 0 trigonal, there is no lone pair. 3 0 trigonal planar. 3 1 ammonia NH3. 3 bond pairs and 1 lone pair. Why? This is pyramidal. Why is ammonia pyramidal? Because of lone pair bond pair repulsions. 3 2 T shape ClF3. It is a T shape. Don't worry about the lone pairs. While writing the shape, only these 3 are considered. While writing the shape, only the nucleus, chlorine nucleus, fluorine nucleus, another fluorine's nucleus, another fluorine's nucleus. How they are relatively arranged to each other, only the nuclei are considered while considering the shape. Only the nuclei are considered. Arrangement of electron pairs, that is different. There you may include lone pairs also, because you are talking about electron pairs. Arrangement of electron pairs, you can take both bond pairs and lone pairs. But as far as shape is concerned, only the nuclei are considered, respective positions of one nucleus from the other, relative positions of the nuclei. So tetrahedral, we have many examples. Methane, SO4 2 minus, 4 bond pairs, 2 lone pairs. NH4 plus, once again 4 bond pairs, 1 lone pair. Sorry, 4 bond pairs, no lone pair. All of them belong to 4 0 4 0 4 0 4 0 4 0. 4 1 distorted tetrahedral. Distorted tetrahedral you will find in SFO, 4 bond pairs, 1 lone pair. So you have 2 fluorines in a straight line and 2 fluorines arranged like this in a V, and of course there is a lone pair. So this is called distorted tetrahedral or seesaw. XeO2F2, XeO2F2. Once again there is a lone pair, XeO2F2. The question given in 2012 IIT. The shape of XeO2F2 is seesaw. But what is that you should remember? You should only remember that it has a lone pair, 4 bond pairs and 1 lone pair. 4 guessed atoms, 1, 2, 3, 4. Don't look at the number of bonds, only guess 1, 2, 3, 4. 4 bond pairs, 1 lone pair. Square planar, XeF4. 4 bond pairs, 2 lone pairs, XeF4. PCl5, trigonal bipyramidal, 5, 0. BrF5, 5, 1, 5 bond pairs, 1 lone pair. 6, 0, SF6, 6, 0. There are many octahedral molecules. In fact, tetrahedral and octahedral are the most preferred geometries. PCl6 minus, SiF6 2 minus. So there are so many anions like that. AlF6 3 minus, octahedral. XeF6, even after forming 6 bonds, there is a lone pair, 6, 1. It will have a capped octahedron, an octahedral which is capped or which is distorted. So IF7 is pentagonal bipyramidal. 7 bond pairs, 7 guessed atoms, I repeat, 7 bond pairs and no lone pair. Okay. Now we will look at some of the questions. Now let us look at some of the questions given in past exams. You have the question on your screen now. Which one of the following is a correct set? The question is about H2O. Let us write whatever we know about H2O. H2O, we know that it is 6 plus 2 by 2. 6 plus 2 by 2, 4 sp3. The hybridization is sp3 and it is angular. Therefore, the answer is 1. H2O sp3, the answer is 1. What about the other options? BCl3, it is 3 plus 3 by 2. 3 plus 3 by 2 means it is sp2, it is not angular. NH4 plus, the hybridization is sp3 and it is not square planar. NH4 plus, as we have already seen, is tetrahedral. CH4, once again, it is tetrahedral, but the hybridization of CH4 is not DsP2 as it is given in the one of the options. CH4 is sp3, 4 plus 4 by 2. Let us go to the next question. The compound in which the number of d pi p pi bonds are equal to those present in ClO4 minus. First of all, you should know about ClO4 minus. ClO4 minus, you have 3 d pi p pi bonds. This is a d pi p pi, this is a d pi p pi, this is a d pi p pi. How do we know? Look at the electronic configuration of chlorine, 3s2, 3px2, 3py2, 3pz1. So in this state, chlorine can form only one bond. For it to form 3 pi bonds, it has to go to the excited state. All of them should be excited and it will become 3s1, 3px1, 3py1, 3pz1, 3d1, 3d1, 3d1. So now only chlorine can form 7 bonds, out of which all 3 pi b pi bonds are. So it has 3 d pi p pi. I told you we need pure orbitals for pi bond formation. Therefore, you have 3 d pi p pi. Among the options, you have XeO3. XeO3 has 3 d pi p pi bonds, just like this. XeO3 also has 3 d pi p pi bonds. XeO4 has 4 d pi p pi bonds. ClO4 minus has 3. XeF4 no pi bond at all. XeF4 no pi bond, no question of any d pi p pi bond. XeF6 also no pi bond. Therefore, d pi p pi, the question doesn't even arise. So you have XeO3 and XeO4, among which XeO4 has 4 d pi p pi bonds. If you write its electronic configuration, you will come to know. You practice the electronic configuration of xenon. So the answer on your screen says it is XeO3. Next question. Which of the following is not tetrahedral? It's very simple. Tetrahedral, it should have a minimum of 4 pi bonds. Sorry, it should have a minimum of 4 guest atoms. You look at CO3 2 minus, it can never be tetrahedral because it has only 3. All others have BF4 minus, NH4 plus, SO4 2 minus. Therefore, the answer is 3. Carbonate is not tetrahedral. And what is carbonate? Carbonate is trigonal planar. Why? 3 bond pairs, no lone pairs. It is not tetrahedral, and that serves our purpose. That is the answer. But you should know what shape this one is. All others being tetrahedral, this one is 3 bond pairs, no lone pairs. You go back. Next question. Which of the following is linear molecule? BeCl2, 2 bond pairs, no lone pairs. H2O, 2 bond pair, 2 lone pair. H2O, 2 bond pair, 2 lone pair. It can never be linear. It can never be linear, I repeat, because the lone pairs drive it mad. SO2, double bond O, there is a lone pair. So, 2 bond pair, 1 lone pair cannot be linear. Methane, tetrahedral. Therefore, the answer is BeCl2, which is linear. BeCl2. Next question. Which one of the following is a correct set? I think we have answered a similar question. H2O, I think it's a repetition in fact. Let's go to the next question. What is the hybridization state of the central atom in the conjugate base of NH4 plus? I think this question has little connection with the topic, ionic equilibrium. So, what is the conjugate base? NH3. So, NH4 plus conjugate is NH3. These two are conjugates. They play in tandem with each other. NH3 takes a proton, he gives a proton, vice versa. Therefore, NH3, the hybridization of NH3, 5 plus 3 by 2, 4 sp3. The answer is 2 sp3. Next question. The number of lone pairs present in XeF4, we already did this. XeF4, 8 minus 4 by 2, 2 lone pairs. The answer is 2. Answer 2 lone pairs. Fourth option is the correct option. Next question. Which of the following statements is true? Hybridization of the central atom in ammonia and CH4 is sp2, which is wrong. NH3, it is sp3. CH4 also, it is sp3. BeCl2 has V shape. No, BeCl2 is linear. SF6 is octahedral and FSF bond angles are 90. That is correct. CO2 has dipole moment. That is wrong because CO2 has no lone pair and similar terminal atoms. So, we discuss polarity at a different time. But right now, the answer is 3. SF6 is octahedral. Next. Which of the following has the lowest bond angle? H2O, the bond angle is 104.5, less than the tetrahedral angle 109.5. Pyramidal, so this is tetrahedral. Pyramidal will be slightly less, 107, and bent will be further less. So, CH4, it is tetrahedral 109.5, and H2S, the bond angle is just 92. So, this has the smallest bond angle. The answer is option number 3. Which one of the following has the lowest bond angle? No, the answer is wrong. The answer should be, answer is H2S. Answer given on your screen will be corrected. Which of the following is the correct pair? BeCl2 linear, NH3 linear, CO2 tetrahedral, BF3 octahedral. Which is correct? BeCl2 is linear is correct. NH3 can never be linear because, because NH3 is can never be linear because it is the 3 bond pairs, they can't be on the same line. So, the answer is BeCl2 linear. Next question. Which of the following covalent molecules is an exception of octet rule? Obviously, BeCl2, it has just 2 electrons, 2 plus 2, 4. 4 means less than 8, less than the octet. The answer is BeCl2. The answer is BeCl2. Next question. The state of hybridization of boron in BeCl3 is BeCl3. Straightforward question. 3 plus 3 by 2, 3 sp2. What is this B? Third group, 3 valence electrons, sp2. The answer is sp2, second option. Next question. The effect of repulsion between the two lone pairs of electrons present on oxygen in water molecule is, okay, what happens because of repulsion? If there are no lone pairs, if there were no lone pairs, HOH would have been linear, the bond angle would have been 180. Because of repulsion, it has acquired a shape, okay, 104.5 because of the lone pairs only. Therefore, the bond angle decreases. The correct option is decrease in HOH bond angle. Next question. Which of the following contains a coordinate covalent bond? I gave you very much. If you have a plus or a minus, you should first smell a coordinate covalent bond, plus or a minus. Here we have one clear cut case, NH4 plus, just NH4 plus, that is the answer. Answer 3. Next, D2sp3 represents which of the following? D2sp3 means all in all you have D2sp3, you have 6 orbitals and they will be arranged only, 6 can be arranged only in an octahedral manner. So, the answer is octahedral. Answer 4. Okay, thank you. We will meet in the next lesson.